Hey y'all, today we're going to be talking about how to find the area between two curves. Now we've already dealt with finding the area underneath one curve, and that dealt with integration, so we'd expect our answer to deal with integration for here as well, and indeed you'd be right. Let's dive in. Let's consider the following example. Now I've drawn two functions, the red function which we're going to call f of x, and the blue function which we'll go ahead and call g of x. Now let's say that I want you to find the area between these two functions, right in here. And moreover, let's say I want the area to be kind of bounded by these two lines right here. Let's say this is the line x equals a and x equals b. So I really am kind of thinking about this big blob right here. What's the area of that? Well, this might not seem so clear on the surface as to how to do it, but it turns out integration is your friend. For instance, if I were to find the integral from a to b of just my regular function f of x, my top function, turns out that thing would give me this entire area in red. All the way down to the x-axis. So that gives me the red area. A sub dot red. If I do the same game from a to b with my bottom function g of x, that will in turn give me the blue area, kind of signified right here, from g of x on down to the x-axis. Now notice the following. If I want to find my total area, as in this area kind of highlighted in black, I know my picture's getting crazy, all I have to do is take the total area and subtract off this blue portion of it. But we know exactly what the total area is and the blue portion is. That's just the red area minus the blue area. Now we can end up simplifying by subbing in. This is just the integral from a to b of f of x minus the integral from a to b of g of x. Now since they have the same bounds of integration from a to b, we can actually combine this into one integral, the integral from a to b of my top function f of x minus my bottom function g of x. And this right here is exactly how we're going to find our area. It will always be the integral from your left bound to your right bound of top function, so more generally, the formula we'll be using, from a to b, our left bound to right bound, of our top function minus our bottom function, all with respect to x. Let's dive into an example as to how to use this formula. Let's go ahead and start with an example of finding the area between the curves f of x equals x squared and g of x equals x, all between 0 and 1. Now first, a picture will help, so a graphing calculator will be useful in this section. Now I'm worried about between 0 and 1. Between there, our functions will look like the following. F of x, I'll signify in blue, will be kind of the start of the parabola. While g of x is just g of x equals x, so we'll just have a line kind of going like this. As we're only curious about what happens between 0 and 1, x equals 0 and x equals 0 and x equals 1, that shows that we really care about this area right in there. So now we have to ask ourselves, how do we get that area? Well, remember the setup will always be the integral from your left to your right, we'll signify that as a to b, of our top function minus our bottom function, all with respect to x. Top minus bottom always. In this case, our left endpoint is 0, our right endpoint is 1, taken from x equals 0 and x equals 1, and our top function in red is g of x. And our bottom function in blue is f of x, so x minus x squared. All with respect to x. Now I'm being a little crazy with these parentheses, but that's because this negative might distribute if your bottom function's a little bit more complicated. From here, integrate as regular. This is going to be 1/2 times x squared minus 1/3 x cubed. Evaluated from x equals 0 up to x equals 1. All we have to do now is solve the definite integral. This is just plug in the top number, 1/2 times 1 squared minus 1/3 times 1 cubed minus 1/2 times 0 squared minus 1/3 times 0 cubed. This side ultimately becomes 0, leaving us with 1/2 minus 1/3, which gives us an answer of 1/6. A good picture will help, but then just remember left to right, those are our bounds, and then ultimately top minus bottom function. Let's dive into another example. Let's move on to another example. In this example, find the area between the curves f of x equals 1 over x in red and g of x equals x cubed in blue between x equals 1 and x equals 3. So when we're looking at the area in question, if I draw on the lines x equals 1 and x equals 3, and then we picture the area between the curves, we must be looking for this shaded area right here. Now remember, in order to find this area, all we have to do is take the integral from your left endpoint to your right endpoint of the top function minus the bottom function. So the area will be the definite integral from 1 to 3, left to right, of our top function, x cubed, minus our bottom function, 1 over x. Now, as I said, I'm being a little bit extra with my parentheses, and that's because this negative will distribute if this term is a little bit more complicated. So no need to write them in this problem. From here, we just go ahead and integrate. This thing's as simple as it gets. So we do just a power rule right here, giving me 1/4 x to the 4th minus 1 over x. The integral of that is just the natural log of x, the absolute value of x, that is. All evaluated from x equals 1 up to x equals 3. From here, plug in your top number, 1/4 times 3 to the 4th minus natural log of 3, and subtract it from your antiderivative with the bottom number plugged in. 1/4 times 1 to the 4th minus the natural log of 1. And you don't need to write the absolute value bars on the logarithm because both of these numbers are positive. When we go ahead and simplify this out, we'll get 81 over 4 minus the natural log of 3 minus 1/4, and then the natural log of 1 is just 0, so we can leave that off. This gives us 80 over 4, 81 over 4 minus 1 over 4, or, better yet, 80 divided by 4 will give us 20 minus the natural log of 3. And that will be the area between the curves. Next time we'll be getting in to how we can figure out this area when we don't necessarily have a pretty picture, when I just give you two functions and that's it. Now let's tackle the situation of finding the area enclosed completely by two functions. Let's consider the example as just an idea of how these problems will look. Find the area enclosed by the functions y equals 5x minus x squared and y equals x. Well, in this case, it turns out that we don't have our left and right endpoints given, along with the problem of figuring out which is top and which is bottom. This is all complicated by the fact that we do not have a picture. If we did want to picture this, we could actually have a function that looks something like this. This being y equals 5x minus x squared, and then last but not least, y equals x is the line we all know and love, the identity map. If we had a picture, it'd be pretty easy just to notice, hey, we're after this area. However, it's still an open question as to how to gather which x's we're worried about, what your left endpoint and what your right endpoint are. The thing to notice here would be that we can actually find these endpoints by setting the functions equal to each other. Your bounds of integration will be exactly where these two functions intersect. So, to solve the problem, first off we want to find our endpoints. Set 5x minus x squared equal to x. From here, solve it out. I'm going to add these guys over this way to get a positive x squared term, giving me x squared minus 4x equals 0. From here, go ahead and factor out an x. X times x minus 4 equals 0, giving us ultimately x equals 0 and x equals 4. Now it's pretty easy to tell by the picture that our red function will end up being the top function. However, if you don't have a graphing calculator, this can prove difficult. One way to figure this out would be to actually take a test point in between. If I plugged in, let's say, 1 into my first function, so maybe I call this y sub 1 and y sub 2 to distinguish them, y sub 1 with 1 plugged in it will be 5 times 1 minus 1, or 4. Y sub 2 with 1 plugged in it just gives me the answer of 1. It just gives me 1 back. From here we can make a judgment call and say, hey, 4 is bigger than 1, so therefore y1 is top and y2 is bottom. The reason we're discussing this is if you do not have a graphing calculator and can't get your hands on these pictures, we need some way to gather which function's on top, and this is your best bet. Now that we have our left and right endpoint, as well as which function is top and which function is bottom, we can go ahead and find the area. The area is still the integral from the left endpoint 0, up to the right endpoint 4, taken from our endpoints, of our top function, 5x minus x squared, minus our bottom function, x. This thing, once we simplify out the inside, it always pays to simplify out the inside, will just be the integral from 0 to 4 of 4x minus x squared with respect to x. From here we integrate. This gives me a 2x squared minus 1/3 x cubed, two basic power rules, evaluated from x equals 0 up to x equals 4, which, if you notice, by plugging in 0, I'll just have 0. So really our answer will just be 2 times 4 squared minus 1/3 times 4 cubed. 2 times 4 squared, well 4 squared is 16 times 2 is 32. 4 cubed is 64, so 32 minus 64 over 3, which will ultimately give me an answer of 32 over 3. Yet again, these answers should be positive. If we're discussing an area, you have to have a positive number for area, or at least 0 perhaps. But, so if you ever get a negative, the thing you should be looking for is, did I have my top and bottom function right? This is our best way, if you don't have a graphing calculator, of actually figuring out the setup for these types of area problems. An important thing to note is that we always must maintain this top minus bottom relation. if you are ever finding a problem where the top function and the bottom function switch places, i.e. they intersect, we actually might need more than one integral. To consider an example of this, let's look at the following. Find the area completely enclosed by f of x equals x cubed minus x and g of x equals 0. To give us a picture of this, if I were drawing f of x, x cubed minus x in red, and g of x in blue, our setup will look something like this. That's f of x equals x cubed minus x, and then g of x in blue is just a line y equals 0, which is the x-axis. Now, as we're finding the area completely enclosed by these two functions, we notice that we have two separate cases of this now. We have the area over here in green, but then we also have this area. As I have two different scenarios, one where red is on top and one where blue is on top, it turns out that I need two separate integrals. Let's call it I1, integral 1, and I2. And that is because top and bottom must always be maintained. Now, in order to figure out these endpoints of these integrals, here, here, and here, we follow the advice from the previous slide. So first off, to get our endpoints, set the functions equal to each other. X cubed minus x, f of x equals g of x, and hey, g of x is just really nice this time. In order to solve this, first off, factor out an x, giving us x times x squared minus 1 equals 0. And ultimately, setting them both equal to 0 and solving, we would get that x equals 0 and x equals plus or minus 1. Now, this is where I would really recommend a graphing calculator or just any kind of graphing device at all, because having the picture in front of you is a lot easier than having to try to figure out which is top and bottom on its own. But one thing we can still try to do is take test points kind of in between these different endpoints. So this is kind of an assumption that we would be having two integrals right here. So maybe one thing we could test would be f of negative 1/2 compared to g of negative 1/2. And then we could test f of positive 1/2 compared to g of positive 1/2. As you can see, this gets to be a little bit tricky and not so clear, so really a graphing calculator ends up being your best bet. F of negative 1/2 gives me negative 1/8 plus 1/2, while g, which is greater than 0, g of anything is just 0. F of 1/2 gives me 1/8 minus 1/2, which is less than 0, and g of 1/2 gives me 0 again. So if we couple these two things together, we can tell in this scenario, as f is bigger than 0, that f is top. Versus down here, 0 is going to be bigger than that guy, so g would be top. Yet again, try to get a graphing calculator. This is much simpler, just to observe it. I do want to see that work, though, for the endpoints. Now we set up our area integral. Since we have two scenarios, here and here, we need two different integrals, which we've named I1 and I2. Now I1 is just going to be the integral from our left endpoint to our right endpoint, so from negative 1 to 0, of our top function, and over here f of x was on top, as evidence shows right here. So of x cubed minus x, so the top function minus the bottom function, g of x, so minus 0. That's I1. plus I2, the integral from 0 to 1, left endpoint to right endpoint, of our top function, g of x, 0, minus our bottom function, f of x, minus x cubed minus x, all with respect to x. From here, the parentheses don't really matter on this guy. We get the integral from -1 to 0 of x cubed minus x with respect to x. However, over here, the negative and the parentheses play a huge role, giving me, upon simplification, the integral from 0 to 1 of minus x cubed plus x. From here, we go ahead and integrate, giving me a 1/4 x to the 4th minus 1/2 x squared, solved from x equals -1 up to 0, plus, and we get the kind of the same antiderivative with some negatives flipped, -1/4 x to the 4th plus 1/2 x squared, solved from x equals 0 up to 1. Now I'm putting these brackets around because it's important that we solve these out individually and then add their answers together. So for instance, if I plug in -1 over here, or 0 over here, I'll get 0. So we get 0 minus, and then now plug in the bottom number, -1. We'll get 1/4, and then minus 1/2, plus our top number plugged in over here. So plugging in 1 will give me -1/4 plus 1/2, minus our bottom number plugged in over here, which is just 0 again. If you allow me to finish the problem up here, we have 1/4 minus 1/2 giving me -1/4, but we're subtracting it. So in that first parenthesis, or that first bracket, we'll just get positive 1/4. Plus, in our second brackets, -1/4 plus 1/2 will give me positive 1/4. Ultimately then, upon adding, we find that our area is 1/2. Two morals of the story. 1, always maintain top and bottom, top minus bottom. A graphing calculator helps you to determine if switches are going to happen. And then second moral of the story is really take your time on these things. These things can be really tedious, especially if you switch multiple times. However, hopefully the algebra ends up not being too bad. Show your work on the endpoints, and really good luck on these problems. They tend to be a lot of fun. Now let's talk about a business application to find the area between two curves, and this comes up through the consumer and producer surpluses. So let's start with an example. Say I have this dingy pink iPhone for sale, and I said, hey, how much would you be willing to pay for this, assuming you wanted to buy it? Let's then say you offered $100, and I said, ha, I would have been willing to sell it for $50. That $50 of extra money that I had is going to be what we call the producer surplus. In a similar manner, even though you offered $100 and let's say I sold it to you for that, maybe you said, ha, I would have been willing to pay $200 on it. Well, that hypothetical $100 that you pocketed is what we think of as the consumer surplus. Graphically speaking, let's say we have this market characterized by this supply curve and this demand curve. Now we already know how to find the equilibrium point, which occurs right here. The equilibrium quantity signified by x sub e, and the equilibrium price signified by p sub e. It turns out that our consumer surplus will be represented by this area right here. And it turns out that our producer surplus will be represented by this thing right here. Now we already have a way of figuring out the area between two curves. So let's go ahead and try to get formulas for these. Our consumer surplus will be the integral, or will be just this area in green. So our left endpoint is 0. And our right endpoint is the equilibrium quantity. And then we do top function minus bottom function. Our top function, the red function, is our demand function. Our bottom function is actually this solid black line. Now that black line can be signified as a line y equals P sub E. So all we have to do is subtract off the equilibrium price. And then integrate with respect to x. Our producer surplus can be found in a similar manner. We take the integral, since we're represented by this area, take the integral from our left endpoint, still 0, up to our right endpoint, the equilibrium quantity, and then figure out top function minus bottom function. Our top function in this case is our equilibrium price, and our bottom function, this blue line, is the supply curve. And then last but not least, integrate with respect to x. Let's go ahead and see some examples where we actually give some mathematical definitions to a demand function and a supply function. Let's go ahead and now consider the following example. Find the producer and the consumer surpluses if demand is given by P equals negative 0.36x plus 9 and supply is given by 0.14x plus 2. Well, if we're going to go ahead and find these guys, first off we do have a formula. That formula depends on us knowing both the supply and demand functions and then also the equilibrium point. We're not given the equilibrium point, so we have to solve for it. We solve for the equilibrium point by setting the two functions equal to each other. Negative 0.36x plus 9 equals 0.14x plus 2. Maybe adding this over and subtracting over the 2, we'll see that 7 equals 0.5x. This ultimately gives us an equilibrium quantity, x sub e, of 14. Now in order to get our equilibrium price, plug in the equilibrium quantity to either your demand or your supply function. The reason it will give you the same answer is because we just solved for where those two graphs intersect. So they should have the same x and y value. So plugging in to, let's say, our supply function, 0.14 times 14 plus 2, we should get an answer of 3.96. That's our equilibrium price. From here, we just need to plug into our formulas appropriately. Let's start with producer surplus. Producer surplus was given by the integral from 0 up to your equilibrium quantity, 14, of your equilibrium price, 3.96, minus your supply function, 0.14 x plus 2. Simplifying out, what we end up with is just the integral from 0 to 14 of 1.96 minus 0.14 x, all with respect to x. If we go ahead and work this out to its totality, because now I'm assuming we know how to do definite integrals, you should get an answer of $13.72. Just remember your basic power rules. Our consumer surplus is found similarly. Consumer surplus was given by the integral from 0 up to our equilibrium quantity, so from 0 to 14, of our demand function, so function first times, negative 0.36x plus 9 minus our equilibrium price, 3.96. We could go ahead and simplify this out. For instance, in this case, we would get the integral from 0 to 14 of negative 0.36x. And then we have 9 minus 3.96, which will be plus 5.04, all with respect to x. And then ultimately, upon simplifying and actually computing this integral, what we would get is an answer of $35.28. Notice these answers are in dollars because we are talking about kind of a surplus extra money in your pocket. Hey y'all, thanks for tuning in today as we explore the area between two curves and how to find said area. Remember, in order to find the area between two curves, it may be bounded on the left and right by certain x values, you need to just integrate. Now our integral was always set up to be top minus bottom. If those functions switched places, one switched from top to bottom and vice versa for the other, we needed multiple integrals. Top minus bottom must be maintained. In pursuit of this, we might have had to find endpoints to integrate by, we might not have been given them, in which case you just set your function equal to each other and solve out for x. Lastly, we talked about the business application of consumer and producer surpluses. These were just special areas between curves, which we found through the formulas consumer surplus equals the integral from 0 to our equilibrium quantity of demand minus our price, while the producer surplus is found by the integral from 0 to our equilibrium quantity of price minus supply. We might have to find the equilibrium point in this case, but that's not a problem. Set your demand function equal to your supply function and solve out for x sub e. From there, plug in x sub e to any function, demand or supply, to get your p sub e, and then you can solve the integral. With that being said, good luck on your homework, email me with any questions, and thanks for watching.